But you're going to give a tutorial on the things that you do know, which is quite a lot. And now focus on extended implementation.
Thank you, Jens. Yeah, so the goal for this is just to give people a sense of the basic programming model behind X10, an introduction to some of its features, just to give you a sense of what the language is like and a little bit of a sense of its implementation. The implementation is at a fairly high level. I'm not going to dive down into low-level stuff. I'm very happy to talk about that if people want to. And there's a small group here. Any questions? Try to make it interactive. Try to make it fun. And so I think basically I have about 35 or 40 minutes of slides to give you just a sense of X10, and then about 5 or 10 minutes of the kinds of things we're doing with X10 now, just to give you a little sense for some of the things that are going on in the X10 world at IBM. And then we're going to find out a lot about things that are going on in the community today. So it's just a chance to try to find out what's going on. Okay, so just as Dan, so the X10 started back in 2004. I wasn't there then, but the genesis was really came out of this DARPA high productivity computer system. So unlike most DARPA things, the P there stands for productivity, not performance. And so the big challenge here is they looked out in the future and they saw that large-scale parallel machines were going to become increasingly harder to program. And these large-scale supercomputers, they're clustered systems where you've got thousands of effectively SMP, symmetric multiprocessor computers connected by a high-performance interconnect. There's large aggregate memory, disk storage, etc. in these systems. So the system is built out of all these components. And so the question is, how do you effectively program something like this? And the feeling was the current sort of MPI-based systems were probably reaching the end of their lifetime, although they're still going strong. But as the goal is to try to make it more accessible for more people. And so IBM came out with the X10 language as part of this program. The Chapel language from Cray came out of the same program, and also the Fortress language from Sun. So there's a push from all three major vendors involved in this to try to come up with a higher level, more modern programming language for programming these things. So that's from some supercomputing back in 2004. That's what the systems looked like and where they're going, and that trend is, that roadmap's continuing. They're like that. But I think the thing that makes X10 more interesting now is if you sort of look at, flash forward a few years, we have a rise of big data, and HPC is moving out to the commercial world. There are lots more people trying to do things that 10 years ago would have been classified as HPC-like computing, and they're not all have the skills or the ability to program in a very low-level language like C or MPI, and there are things they're doing that just doesn't make sense for them to do that. But these commodity clusters are very similar to supercomputers. You've got thousands of nodes, they're SMP nodes, they're connected by a high-performance network, not an internet, so there's some interconnects, there's some subtle differences there. But really the programming model problem is very similar. You're dealing with distributed memory, and you want to run a computation across a bunch of nodes in a distributed memory system, and you want to do that without getting down into low-level grunge of C and MPI, or Fortran MPI, or C++ and MPI. You don't want to deal with MPI if you don't have to. Right, so what is X10 trying to do about this? So the approach the X10 project took was to take a Java-like language and add features to it to support concurrency, so finer-grained concurrency, to scale out across these kinds of systems and to deal with heterogeneous systems. So trying to deal with programming CPUs and GPUs. And try to take some of the commercial productivity gains from the 90s and the early 2000s that arose in the Java ecosystem and make them applicable to this kind of computer system. So try to make them easier to program for more people. So it's Java-like, and you have scale out, you have fine-grained concurrency, so the nodes, not only do you have a lot of nodes, but the nodes also have a lot of hardware threads, and so you have to both program concurrency within the node and distribution across the nodes. Right, the goal is to get a programming model that spans several of these levels, so you don't have to sit there and program in C++ plus CUDA plus OpenMP plus MPI, because that's very challenging to have all those programming models going on and dealing with that. Okay, and also we wanted to get some. Also, one of the goals is, initially this project is about a new programming language. But also, as you sort of get to the point of trying to get people to use it, you realize you need some kind of migration path too. So something we've been working on the last couple of years and working to continue to work on is make it possible to write an application that's a mix of new code written in X10 plus old code written in your existing language, whether it's Java for the commercial space or C plus some native code plus MPI for your HPC space. And so we've been doing a lot of work with Java interoperability that we're going to talk about a little bit today. and to enable use of C and C++ libraries as well. Okay, so that's sort of the project goal and what we're trying to do. So what I'm going to try to do now is I'm just going to talk about some of the language concepts, give you a flavor of the language, not get into any of the compiler or language lawyer kind of details, just give you a flavor of it, talk about the implementation, and then finish off with a few minutes of what's new and exciting that we're doing now that we think would be interesting to you. So at the core of the X10 programming model is this notion called a partition global address space. And what this is doing, there are a variety of languages in this family, but the key idea is that you're going to be running your computation across a computer that has distributed memory. And we feel that it's just not productive actually to completely hide that from the programmer. The difference between memory on a local node and memory on a remote node is so significant from a performance sense that has to be exposed somehow. But you also, it's very convenient to have an illusion at least of a global address space. So where the languages in this family fall down is, or take the approach of, they allow the programmer to think as if there's a global address space. So you're allowed to have pointers that cross between machines, that's what these arrows are supposed to indicate. But there's some notion of locality or partitioning. And so you have an awareness of memory that's local to you and memory that's remote to you. And even if you have a pointer to remote memory, it's more expensive to dereference that pointer than it is to dereference a local pointer. So that's made part of the programming model. And the exact details of how this happens are different in these different languages. Some of them take the view that this should all be implicit, and so the compiler on the runtime will just magically generate code for you to access a remote pointer, send a message to some other machine, get the data, bring it back, do something to it. That's where most of these languages are. X10 is actually a little bit unusual, and it takes the model of the programmer has to explicitly go to the place where the remote object lives and access it there. Right? So I think it's the only one of these languages that doesn't sort of do that for you under the covers. And so that was a decision we made because we feel that the performance implications of that are so large that the programmer, it should be explicit in the program text to help the programmer see what they're doing. But at the same time, there's a lot of this that can be automated by the compiler and the runtime system. So we make it very, very easy to do that, but we make you do it explicitly. And that's where X10 is philosophically. And there's some of these other languages are in different places. And then, it's possible to imagine taking a version of X10 that does this implicitly and compiling it into an explicit X10, or building a higher level language on top of X10 that hid this for you. But that's where the programming model is.
I have a question.
Yeah. Go ahead, Jens.
Good. I have been hoping to ask for almost a year. Okay, so it dawned on me at some point here that this whole question of accessing pointers on the other places, as you call them, is kind of an independent problem of parallelism, isn't it? That one can sort of think out one single-threaded computation that accesses data here and there, and it doesn't really matter whether it's parallel or not. What matters is that the data is not here. Right. And so I have now a chance of making a mistake.
Yes.
Isn't that?
Yeah, that's right. Yeah, it's definitely, there's the whole concurrency aspect of it, and then there's the data somewhere else. And so
that's a different aspect.
So it's really an orthogonal concern, but they're sort of get coupled together.
They do.
Okay, so in terms of how this maps into X10, as in says we have places. So the partition of the address space in X10 get mapped to places. A place, you can think of it as a process, or a typical Unix process, or as an MPI rank. It's not exactly the right way to think of it in terms of the high-level programming model, but that's how it's implemented. And so you should sort of think of that way as sort of an intuitive understanding of what's going on. So place is really a unit of memory that can be addressed by the things that are running within that place, the threads of control. In X10 we call those activities. You can think of an activity as a thread, or to some level of approximation. It's meant to be a lighter weight task. So what the runtime is actually going to do is it's going to take these activities and multiplex them onto a smaller number of hardware threads. So creating a new activity is a later weight activity than spawning a new P thread. But if at the level of abstraction, these are threads of control that are doing things, and what they're doing is operating on their stack in their local heap. Okay? And we can have these the cross-place pointers. We call it global ref in X10, or global references. Some things get a little abbreviated in the class hierarchy, but global references is what they're called. And in terms of language constructs, as Jens said, really there's the concurrency aspects of it, and so concurrency in X10 is dealt with by basically 2 or 4 statements, depending on how you want to count them. So we add async s. So async s creates a new activity that runs in parallel with the current activity and executes the statement s. So that's how you spawn off a new thread of control. Now finish s is how you do sequencing. So the activity that executes finish will not execute the statement after the finish until all the activities that have been spawned by s recursively have terminated. So this is a way to sort of say, I'm going to do something. That internally may have a whole bunch of parallel work it's going to do, but when all of that is done, I'm going to go on to do the next thing. So that's sort of creation and control of concurrency in X10. And we also have, within X10, there's a atomicity. So how do you deal with people actually wanting to share, to mutate, multiple activities wanting to mutate data in the same local heap? The language mechanism in that, for that in X10 is atomic. So atomic s means do s atomically with respect to all other atomic statements in that place. So atomicity within X10 is just within a place. We don't try to do a global atomicity across the entire computation. That's just, we feel it's too expensive. So we just give you atomicity within a place. And then when CS is a conditional atomic. So atomically, when this condition is true, do s. And both of these have a weak atomicity property. They're only atomic with respect to other atomic and when statements. They're not atomic with respect to other things that are going on that aren't doing atomics. Yeah, go ahead.
Would it be correct to say that for a particular place, I'm looking at atomic here,
Yep.
that for a particular place there's one lock, and when I execute atomic I have to acquire that lock, and then I execute atomic. So maybe you implement it differently, but would it be correct to think of it that way?
From a semantic sense, that's correct. And that unfortunately is actually also how we implement it.
I see.
So if your places have a relatively low number of hardware threads that are multiplexing a large number of activities, then the fact there's a global lock for atomics is not so bad. If you're running on a very large scale system where you've got 32 or 128 hardware threads, and you're using lots of atomics, then your scalability is going to suffer very badly. I think the long-term ambition when this construct was designed in 2004 or 2005, there's an expectation that by 5 or 6 years in the future, there would be some sort of support for hardware and transactional memory. And so this maps nicely to a transactional memory system as well. Yeah. And when that hardware becomes available, maybe a better implementation is possible. There's also been some research work where people have been looking at, can you take, analyze the data that's actually accessed within an atomic and sort of break, coarsen, sort of have finer grained locks, have certain locks to protect certain regions because they don't conflict with any other things. And as a practical matter, if you're doing lots of concurrency, we also have a library class that gives you locks, which is sort of a failure of the language model at some level, but if you're doing practical programming and you're running with a lot of hardware threads, you can't afford to be having a global lock in your hotspots.
So it would be fair to say you're still waiting for the transactional memory people to help you out?
Yes, I think it would be fair to say that if we ever got transactional memory, then this atomic would become much more useful.
Well, I'm sure it's useful, but maybe...
Well, yeah, sorry, useful, much more performant.
That's sure.
And it does perform, if you're with a small number of hardware threads, it's just fine. So there's certain computer ways of deploying X10 where you can use atomic and you don't have to worry about it.
At this level of abstraction, I would like to ask another question.
Sure.
With your experience, your group's experience of programming, how many applications use atomic and how many don't? Or how many use them a lot and how many a little and how many not at all?
I think a fair number of applications use it a little bit, but we've also tried to do is there's some idioms in X10, I'm actually going to show you in a few slides, where there's certain kind of operations you might like to do, like a reduction, or you're doing a parallel fork and join thing and you want to accumulate an answer. Yeah. There are other language constructs, and you could express that as an atomic, and I'm going to show an example of doing that, but there's this other collecting finish idiom, which is a way of getting the reduction to happen without over-serializing. Yeah. And so some of what happens is we do that, use those kind of idioms.
But it's like after Doug Lee's talk Tuesday morning, I'm sort of more confused than ever about how important atomic is or isn't.
Right. Okay. Yeah, I'm not sure. And we also do have effectively the compare and swap, and we built up a few concurrent data structures. With our Java interrupt, we can actually use Java util concurrent, and so there's a mixed kind of thing going on now, where we're not really sure what the rate level is.
But it seems clear that a non-trivial number of applications who benefit very well from atomic.
Yes.
And then there are others where one doesn't have to use it at all.
Right. And they're also, I mean, it's also the kind of thing where if atomic is showing up in relatively infrequent paths, then you can use it. And or if it's, you know, there are only a few threads at a time, it's also not so bad. Okay, so that's concurrency, and then place shifting is the other operation. So how do you know, I want to follow this global reference from here to there and do something, or I want to go to a different place and do something. And there's basically one construct in X10 that lets you do that. You can do at a place, do a statement. You can also do at a place with an expression that you know, takes the value of the expression and returns it back to the place that did this. And these are not concurrent, these are sequential. So the activity at this place that's executing this doesn't add to some other place. Effectively, it suspends at this place, and at the programming model level, the activity goes to the other place, does some stuff, comes back, and resumes here. So actually implemented, obviously, by sending a message to do something there and waiting for another message to come back to continue. And then you can combine these constructs in fairly orthogonal ways. So in particular, what you really want to do is create a new asynchronous activity somewhere else, or think of it as sending an active message if you want to think of it that way. You do at p async s, right? And the compiler and the runtime recognize that all you're doing is trying to go spawn a new activity somewhere else and optimizes for that, and just goes and does it. And along with that, so finish is not a local finish within a single place. Finish is actually a distributed termination algorithm. So if inside of this S, I do an at to another place and I spawn some asyncs there, the finish at the place that initiated this has to wait for the global termination of all the asyncs. So it gives you a very powerful construct to do a bunch of things concurrently across a distributed system and then move on to the next thing when they're done. And the runtime has a fairly sophisticated implementation of that to try to do a good job of doing that.
How is a place defined?
How is a place defined? I guess at the language level or at the sort of the programming model, it's a region of memory, and that shows up in your programs as, it's good transition to this. So it shows up in your programs as there's a class called place, and so you have these runtime values which you can get, which are the current place. You say here, and that gives you back a place structure, which is the current place. And then the place class has methods that let you enumerate over all the places, go to the next place, the previous place. If you have a global reference, which we'll see in a few slides, you can go to the place where the object that the global reference points to lives and does something. So they sort of show up as, that may not be what you're asking.
The question is, if you say it's a piece of memory, does it also contain the stack execution engine or whatever is needed to do the things actually?
Right. I guess you could think of it as a process, as a Unix process would be the right approximation. So it's a memory place. It's a piece of memory plus some threads of control that are running in it, plus the code that they're actually executing, and then all the other associated environment and the rest of that kind of stuff. So this is the Hello World program, which is it's about 7 lines long. This is doing more than Hello World. What this is doing is it's going to, for every place in your computation, it's going to print out a message from that place. And so it's using all these constructs together. So we're a Java-like language, so you have a public static main method. When the program starts up, there's a single activity running in place 0 that executes main. And so here, it comes in, there's a finish, which in this program, all the finish is doing is preventing you from exiting main before all these parallel activities start. But if there was another statement here, it would be preventing you from moving on to the next thing before you finish printing your messages. All right, so then we're going to iterate over all the places. This is a fairly common idiom in X10. The programmer writes are very rarely, in our experience at least, have hardwired number of places. You tend to write code that's parametric in the number of places. And then when you actually run the program, depending on what transport you're using, there are various mechanisms to say, I'd like to have 4 places or 100 places, and this is how I want the places distributed across my parallel machine. Right? But at the language level, or the programming level, you tend to write abstractly in terms of the places. So we're going to iterate over the places. For each of those, we're going to do this at p async combination. So that's the main activity is looping through here, and it's going to fire off a message to each of the other places in the computation to do something. And what they're supposed to do is basically this line of code. So after, it's going to loop through fairly quickly, firing out those messages, and then it's going to wait because of the finish for them to actually terminate. And what they're going to do is they're going to print something out. Right? And one thing that's interesting here is if you notice they're actually printing out a message. I ran it, I said hello, and they're saying hello. And how do they do that? So this line of code here in line 7, the code mentioned arg sub 0. Now args is a variable that's defined in the scope outside of the at block. Right? So args is a variable that lives at place 0, or the place where this computation is running. But I'm referring to it in a computation that's going to run somewhere else. So the compiler does an analysis to figure out what variables are exposed, and it takes those variables and uses them as roots for an object graph, and it automatically generates the code to serialize that entire object graph that's needed by this computation, send it along with the control message to the place where it's going to execute, deserialize it there, so recreate a copy of that object graph, execute on it, and then if this actually was an expression, it would do the same computation on the return. This would have some value it's returning, and you would take that as the root of an object graph and serialize it back. So this is a fairly powerful mechanism to let people transfer data back and forth. In fact, it's so powerful that sometimes you don't realize exactly what you're doing. So I mentioned arg sub 0 here, which is fine, but what's actually going to get serialized is the entire args array, right? Because the variable that's free is args, and we don't do any analysis to try to determine that you actually only wanted one element of it. So in this case, args is probably small, so you don't care. If args was very big, this would be a performance mistake you could make. And there are various kinds of tracing things you can do to the runtime to have it tell you what messages you're sending around that are too big as part of your performance team. Okay, so there are questions about hello world? Yeah?
What's a rail?
Sorry, rail is a type def for, all right, so an X10 arrays are multidimensional, and they're also not required to be zero-based, and they're not required to be dense. So arrays are arbitrary mapping from n-dimensional Cartesian space to values, and rail is the type def for I'm an array that's zero-based, dense, and has rank 1. And that shows up a lot. And so we have it's not a separate class. So it's just the array class with those constraints on its type. But for optimization purposes, it's important to know that. Right. At some point in the past, 2 or 3 years ago, rail was actually a separate class, and we finally got enough sophistication in our compiler, mainly inlining and some type propagation, that we were able to throw out the specialized class and just have a single array class that the compiler would be able to use correctly, generate good code for whenever it can statically know that it actually is a rail. Okay. So now the next 3 or 4 slides, I'm going to show some examples of computing pi by Monte Carlo simulation. It's not a particularly interesting problem, but it has the virtue of fitting on a slide, and I can do different variations of this for sequential and parallel and distributed to just show you how some of the features work together. All right, so just looking at this is the sequential code. Just like Java, we're going to import some classes. We have a main method. We're going to parse n from our command line to find out how many iterations of this thing we ought to run. We get ourselves a random number generator. And then the basic algorithm is here. You get 2 random numbers. You see if they're inside the unit square or the unit circle. Well, they're inside the unit square. So the question is, are they inside the unit circle or not? If they are, count them. And then when you're all done, just apply a little bit of math to find out what the value of pi is. Okay. Is this all right? And so one thing to mention here is that, you notice for local variables, it's a common idiom in X10 to not give types. So we do type inference for local variables. And for these variables, it's not so exciting because this is an integer and this is for local vals. Because of all the constraint types we have, it's actually usually fairly important to not give types for local variables if there's anything interesting over here, because the compiler will infer a more precise type than you're likely to want to write, and that can then help the optimizer later. Okay, so there's sequential Monty pi. So what we're going to do now is I'm going to show you 2 different ways to make this concurrent. This is the slightly uglier one. So what this is doing is we have the same kind of structure, but now I'm going to create a bunch of asyncs in here. So I've got to finish, I'm going to iterate over p, so I'm going to create p parallel activity, so finish for one.pd async. So the main activity will go through this loop, spawning off some parallel activities, then it will stop here. So the bracket isn't lined up very well. And wait for them to finish. And what they're each going to do is they're going to do the same computation as before almost. They're going to accumulate this thing in my result, and then they're going to do this slightly odd-looking thing here, where they're going to atomically update, accumulate that result into a cell. And so what this is doing is this is heap allocating an object that we're going to then accumulate the result of all these parallel activities in. And so that's what's happening here. Yes?
Why do we need to use the parentheses?
Right. Okay, yeah, so this is something about X10 you're either going to like or hate. I go back both ways. We've used the parentheses operator a fair amount. So X10 has user-defined operators, including the user-defined apply operator, which is the parens. And so what apply on a cell does is it dereferences the cell to get to the storage location that it holds. And if you do that on the left-hand side of an assignment, then it's an update. Right? So what this is doing is taking a result, which is a pointer to a heap allocated object, and storing, doing a plus equals of my result to the double that's stored there. Okay? Yeah.
Is it stored in you said if you start main is located at the place 0.
Yes.
So the cell now is also automatically stored in.
Yeah. So when you're right, that's a good question. So I should have said this. When you're executing an activity in a place, all the allocations that activity does are in the current place. The only way to allocate an object somewhere else is to actually shift to that other place with an @ and then it's a local allocation. Right? So basically all heap operations are always to the current place. And if you have an object that's somewhere else, you have to go there to do that.
What would this result bracket be in longhand?
In what? So you could say result dot set, I think, or I think there's a
field there that you're after.
Yeah, there's a field. This is a shorthand for a method that takes it takes a result as an argument and stores it in the field. So this is a shorthand for result dot set of. So what's this doing? Is this a result dot set of my result of comma? What do I have to do? All right. So first I have to get results. So result dot get. Add that to my result, and then store the result back with a result.set.
Okay, I see. So this explains very clearly why that has to be an atomic there.
Yeah, because you're right. You're going to do a read and a write, and potentially there are multiple activities that are doing this update, and so you need an atomic to make that safe. And then down here, this is the get. Right. So it's result. I don't want to divide the cell by n. I want to get the double in the cell and divide it by n. Right, so this is one way to deal with multiple activities updating a piece of memory concurrently. It's a bit clumsy. For this particular pattern, you could use collecting finish again. So what this code was trying to do is I spawned off a bunch of parallel tasks that were trying to accumulate some pieces of results, and then they're going to reduce them into a value. That's a common enough idiom that we have a language construct called collecting finish that does that. And so what's going on here is, so I have finish, but now finish actually takes a value there. And what this is it's something that implements the reducible interface. And a reducible interface provides two things. It provides a 0, and it provides a reduction operator that takes two things of the type of the reducer and reduces them. Okay, in this particular case, I'm using reducible.sum reducer, which is a built-in struct that does a reduction by doing addition, and a 0 element is 0. Now we've made a decision to do this, and so this is actually a constructor for a struct. If this was a class, it would say new reducible.sum reducible of double parens. So this is creating a struct of that class, passing it to the finish. And the other piece of this is we got rid of the atomic and the cell. And what we do down here is when we want to actually give something to the reducer, we offer it. So I say offer my result, and what the compiler on the runtime will do is then take this result and plumb it through to the collecting finish mechanism to take the result and accumulate it into the current things that are done, being added up. And then when the finish terminates, now the finish is an expression. It has a result, a value, which is the reduction of all the things that have been offered. And there it is. We print it. Yes?
Does this offer in any way have an atomic as part of its meaning?
As part of its meaning or part of its implementation? So the offer is...
Let me ask you about the implementation first.
So offer, the idea with this is we've expressed this in a way so there's no unneeded not synchronization, but sort of happen before relationships between any of these offers. And so now the implementation is free to accumulate these various things that are being offered in any way that it wants. And in particular, what the implementation does is there's a set of worker threads that are executing, and each of those, if there's a finish that has a reduction going on, there's a piece of worker thread local storage into which the result is accumulated. So these offers are going on thread local storage without any synchronization, and then when there are no more activities no more live activities associated with that on the worker thread, it gets reduced up to the finish, and that's where the atomicity happens.
So offer works with a variety of things like reducible, or?
Offer works, basically the constraint is, so this reducible, it's a reducible of t of some parameterized type. This particular guy is double, and so this has to offer doubles. I could have had a reducible of hash maps and be hash maps of strings to integers, and offer a hash map of string to integer here, and as long as my reducer had a 0 value, which is an empty hash map, and a reduction function which puts them together somehow and returns another hash map.
I think my point was quite surprised at something that looks like a language keyword.
Oh yeah, so yeah, offer, this is a language keyword.
It is talking to, if you like, something like reducible, which looks like a
right. Well, so
the data structure that I invented.
So the offer is actually talking to the finish.
Okay.
So this particular kind of finish is a collecting finish. So it's a language construct, and within the scope of the dynamic scope of a collecting finish, you can do offers. And this can actually, since this fits on a slide, I didn't do it, but you can actually do a procedure calling here to a method that has a type signature that says it offers things of type T, and within that method you can do an offer, and it will still go off and find this finish. Actually, it's going to crawl up the dynamic stack to find the finish, and statically, it'll make the system will make sure that you can only call a method that's going to offer something in a scope where there's a finish available.
You could offer multiple times.
Yes, in fact, you could also write this code by offering here. I could offer 1 instead of accumulating to my result plus plus. That's, for this particular idiom, that's probably not a great idea because you're going to access thread local storage, and you're not going to contend with anybody, but getting to the thread local storage is going to cost you a lot more than doing integer arithmetic. Right? And so, yeah, so if you're doing something where you have some complicated thing going on and you're going to offer occasionally in various places, you can have multiple offers in finish, and you can be offering multiple times dynamically. It doesn't just have to be once per async.
I see. Okay. So that it will all get reduced.
Yeah, just all gets reduced, and
it's not important that there's one per.
Yeah, no. There can be dynamically. There can be an arbitrary number of these per async, and some asyncs can have none of them, and some can have millions, and it all just sort of works. And it also,
an offer only makes sense inside of a finish.
Right. Offer only makes sense inside of a finish, and in particular inside of a finish that has a reducer. Yeah. So it's basically a thing that's built for this particular pattern, which comes up a fair amount. And it's a way to get this pattern implemented efficiently. One thing that's nice about it is if you want to distribute this, collecting finish just works too. You don't have to change. All I had to do to change from the concurrent guy running in a single place to a distributed guy running across a bunch of places was change my loop. Right? So now instead of creating p-parallel asyncs in the current place, I iterate over the places in the program, add p async, do this, and I'm going to offer. And so what's going to go on here is that each activity in the place is going to be accumulated into its thread local storage. When a place quiesces, so there's no more activities of that place related to the finish, it has to send a message back to the place where the root finish is anyways to tell it a control message. And now we piggyback on that control message the data value that's being provided by this place. So it's a way to accumulate local offers within a place and then sort of send back an aggregation of them to the place of origin, which then reduces them. So we actually have there's some code, computational chemistry code that Josh Milthorpe at ANU has done to do fast multipole computations where he uses collecting finishes to go up and down the boxes of an octree. It's very efficient to do that. Yep.
Okay, well, let me first say that I'm from Denmark, right? In Danish it looks very funny that it says offer, because in Danish that means sacrifice. So I wouldn't sort of expect this my result to still be there. But in any event, so this is of course like a map reduce, where you reduce has the language support right there, but the mapper you're kind of writing yourself with a for loop. Is there a more functional version of this that would be more like the map reduce that people from functional programming sort of like?
There isn't anything in the language yet, and we've talked about trying to take MapReduce idioms and compile them into this, or take this idiom and compile it into a MapReduce.
So maybe you don't need anything new. Maybe you could just sort of write in a style that would somehow do the map, just hack up some functional code. You have procedures and everything.
Right.
And then maybe this reduce it there.
I think this could work out. Yeah, I mean, if you're going to iterate over, so you can do something where you iterated over the elements of a collection in some, where you had some map that you're trying to reduce that you somehow managed to split up into a bunch of pieces and you were going to stuff to it, and that should just work.
That would be homework overload.
Yeah.
The Hello World program, you ran it 4 places. So if you have you run this program with 4 places, it will be split in 4 places. The async was split in the last example by a parameter
that we passed.
Is there a possibility to combine?
Yeah, absolutely. Yeah, so it wouldn't fit on the slide. You could do a 2-level parallelism where you still took that p parameter. I wanted to run p activities per place. You see how you parse that parameter here, and then you do another inner loop here where you do 4 p places at p async, and then you launch off another loop that does async. And so you could do it in 1 of 2 ways. I would probably do it that way: is first launch an activity to each place, and then within the place launch a bunch of activities. You could also do 1 loop that did some kind of modulo thing that launched a bunch of activities from place 0 to the other place. But it's sort of more efficient to spread it out as a tree like that, as a 2-level thing.
Is there a possibility to find out what properties a place has?
Yep, there is. Right now, they're really, in X10, places are fairly homogeneous. So we have only 2 kinds of places. We have normal places, and then we do have some, we can compile X10 to CUDA, or a very small subset of X10 to CUDA to execute on a GPU. So if you're running on a system with the attached GPUs, there'll be some places that are GPUs. And so you can ask whether a place is a CPU or basically a normal place or a GPU place, and then sort of compute back and forth. I think as sort of going forward, we probably need to think about having more information about a place. If you're running a system where your computation, your resources are different. And as the systems get bigger, we're also thinking some about hierarchical places. So it might be useful to think about, I'm a fairly big machine with 128 hardware threads. I don't want to run 128 places. I want to run some smaller number of big places, each within has more things within it that are really sort of maps the NUMA structure of the machine. Might be a way to think about that. Yep, that's fine. This is good.
The async, will it return something? For example, if I have Fortress, there's not similar, but a spawn statement, and the spawn statement gives me some sort of future object.
Right. So in X10, asyncs are, there's no way for the programmer to use an async as an expression, and you don't get an object back you can manipulate. And part of the reason we do that is we have 2 different implementations of async, one of which uses a fork join scheduler. So when you execute the async statement, you're actually creating an object and pushing that on the queue of some worker thread to do it with and eventually execute. We also have a Silk work stealing style thing where we try very, very hard to never actually create explicit representation of the asyncs. And so there, we don't want to be tied into a language model where the programmer can force us to materialize these things which we don't want to materialize to make them run faster. Okay, so I think one more Monty Pie. This is the ugly one. So this is, suppose you weren't using collecting finish, but you're back to using that cell thing I showed you first. How would you do that in a distributed version? And part of the reason for doing that cell one is to show that this one is not that different from that. And basically the key difference is we inject a global reference around the cell. And now when we refer to result down in here, we're not capturing a pointer to the cell object, we're capturing the global reference to the cell object. So we're not going to copy the cell to each place and update it. What we're going to do is when we go to those places, we're going to be sending a reference back to the cell at place 0. And then here, at result, so the global ref has a property called home, which is where it lives. And I could say at result.home, or as a shorthand, I can say at result. And that is interpreted by the compiler as the place I want to go to is the home place of this global reference. So I'm going to go there, I'm going to dereference the global reference to get the cell, I'm going to dereference the cell to get to the double, and I'm going to plus equal it. Right, so this is, sometimes the parentheses get a little out of control when you're dealing with combinations of global references and other things that have operator apply to find out. You can have, I think there are legitimate pieces of X10 code where that could actually go 3 or 4 deep. And then it gets interesting. Yes?
I have a syntax question. The global ref.
I'm sorry, what?
The global ref.
Yeah.
And then you have the brackets. So this the apply function to.
Right. So what this is doing, so we made a decision that so global ref is a struct as opposed to a class. So I didn't talk about the difference, but so a class is a heap allocated thing. A struct is something that's meant to be either stack allocated or inlined into its containing object. And so the struct constructor doesn't say new here. You can optionally say new, but we tend not to try to make it clear what's a heap allocation versus a stack allocation. So this is a global ref of this type, cell of double, and here's its constructor, which takes a new cell of double.
And there are no restrictions, so I could have a global ref which wraps a global ref. Which is not a good idea, but only to...
Actually, you can't. So there is a restriction, which is the global ref. You can put any type here as long as that type is an object. Or an interface. Sorry, it has to be something that's on the heap. I can't create a global ref to a struct because the struct might be on a stack. And I don't want to, if I have a struct-like thing that I want to create a global reference to, I have to explicitly box that.
I see, okay, you want a four byte thing there.
Right, yeah. And the way you can do that is if you, right, this has to be, the global ref contains a pointer. And if you have a struct, you can take a struct and upcast it to any. So any is at the top of the X10 type hierarchy. It's on top of classes, structs, and closures, functions. And so if you have a struct thing which does not have a header, effectively, you can box it to an any to get it onto the heap, and then you can get a global reference to it.
So,
yep.
How is that enforced? Is it just a...
Statically?
No, I'm sorry.
Okay.
More technically, is it just bounded polymorphism?
Sorry, is it what?
Is it bounded polymorphism?
Yes. Yeah. So this is a global ref of T, where T is a subtype of any, or sorry, of object. Okay, so that's the end of Monty Pi. So what I was going to do now is tell you a little bit more about the X10 implementation and some things like that to give you a sense for where that's going. And hopefully this has been enough to give you a sense for the language. At least I think that's where I'm going. Right, so in terms of where we run X10, we really sort of look at the 3 different kinds of platforms we run on. We're trying to run on high-end HPC clusters, so BlueGene is one of IBM's supercomputer, Power 7IH is a Power 7-based supercomputer, basically anything with x86 with InfiniBand or Ethernet in a large-scale cluster. And the goal at the high end really is to let the skilled programmer, and hopefully this programmer doesn't have to be as skilled as they do with CPI and C plus MPI, but the goal is to let someone write some code that's going to perform very well at scale, but hopefully do that in a more productive way. And we can do that for at least some codes. There's sort of a second set of systems we're targeting, which are much smaller, and these are tens to hundreds of nodes, often connected just with an Ethernet. And the goal here is not to compete with C plus MPI, although you can take the codes that you designed to run here and run them there and probably still get good performance, but these systems may not have MPI on them anyways. The goal here is to give main memory level performance. So let the programmer write at something approximating a Java level abstraction, but get the performance of actually using the memory across multiple nodes to do their computation and do that in a fairly productive way. And then we have to target laptops, and we try to perform well there, but the real goal here is to make sure that we're available on everyone's laptop so that there isn't a barrier to entry. Right? You want people to run on Windows, Linux, and Mac so that people can play with you. And we also have some amount of tooling here, so we've got an Eclipse-based IDE called X10DT that runs on all these platforms. And we have a debugger that runs on, integrates the IDE and supports debugging the C++ backend of X10, which I'll tell you about in a minute, on top of Linux. So it's not quite the debugger isn't available everywhere, but the IDE is. Okay. All right, and so in terms of implementations, we actually have 2 different ways we implement X10. So we start with we have a common front end, type checker, and optimizer. And then we're going to take X10 and either compile it to C++ or compile it to Java. We call this one native X10 and that one managed X10. So if in later talks people are talking about native X10 or managed X10, they mean the C++ backend, where we take X10 and compile it to C++ and then run it through the native compiler toolchain to get an executable. Or managed X10 as you run it through a Java backend, generate Java code, run it through a cloud compiler, run it on top of a JVM. So both of these are multi-process, multi-node, except on Windows. The managed X10 on Windows is restricted to a single place, and that's due to the difficulties of, I think I'm going to show you a slide in a minute, but our network layer is compiled, because we use the same network layer on both of these, and on Windows it relies on Cygwin, and we can't get that to work with the JVM very easily. That's X10DT and the debuggers, I mentioned those things. Okay. Right, and this is just a PLDI-related conference. We have to have a flowchart of a compiler just for fun. And so this is showing the compilation and the various backends in the code.
What kind of garbage collector do you use in the C++ version?
Right, so in the C++ version we use the Bohm-Weiser collector, which has the virtue of working. But it does create, obviously the performance model between these two is going to be very different. Right, so for the managed X10 where you have a JVM with a highly tuned generational concurrent collector, and here we've got a collector that does as well as it can, but its performance model is much more malloc-free level of performance than you would get in the kind of JVM level.
And is there, presumably there's a bias the other way in the sense that the computationally heavy code runs faster than the C++ version?
Typically, although there are some pieces of code you can write that run faster than the Java backend, as you sort of get more, this is good at loops, and but virtual functions and stuff scattered across a bunch of classes causes trouble here, and that's what JVMs are good at. So, but yeah, so it's sort of a complicated trade-off space. Right. And so when we're actually running X10, this is trying to show you what the runtime stack looks like when you're running things. You have your application on top. These are sort of vendor-provided network layers at the bottom, and we have a bunch of levels of abstraction. And I think the main thing I wanted to point out here is just that we do run it on top of a bunch of different transports. And TCP/IP is the one that's really good for portability, but performance isn't as good. And these other guys have better performance as you scale up. And then, as much as possible, we've implemented a large part of the actual runtime system in X10. And the motivation for that was when we sort of got serious about the C++ backend about 3 or 4 years ago. We couldn't afford to keep 2 separate runtimes, and the system was mature enough that we could actually write, at this point, this is probably 15 or 20,000 lines of code, and so we can actually get that to go through the tool chains and get our runtime on both backends out of the same source code. And all this sort of interesting implementation of async and finish and add is actually in here. So there's a whole bunch of, there's some X10 classes in the core runtime that implement finish and implement async, and then the compiler will take those source level constructs and lower them into calls against these runtime classes. So if you're sort of curious to see how finish or async works, you can actually go poke through a few classes in here and see most of the guts of it in X10. Okay. All right, so now, so I think that's all I was going to try to tell you about X10, the language and its implementation. And I have a few slides about what things we're doing next. But before we do that, are there questions about X10 that we haven't hit yet? Yeah.
Are you happy about X10?
Am I happy about X10? Yeah. Yeah, I think it's we've been working on it for a long time, and there's been a fair amount of learning as we've used it to actually build our system. People have been around X10 for a while. There's been several disruptive language changes, but we're done with that now, we think. So I think that the core model is pretty stable. And we're actually using it to do some interesting things now. So we're not just writing little toy benchmark programs anymore. We're actually writing significant pieces of code, and it seems to be working.
And the performance is?
The performance is, it's honestly, it's highly variable. So we have codes that we run, that we work on a fair amount, that will run at the same, that get the same performance out of the hardware as a highly tuned C+ MPI core code at thousands of cores. But you can also write code that is sort of misuses some of the language features, and then you have to go through some steps of tuning it. And there is some on the X10 website. There is some advice to people about these are things that work well. These are patterns that perform well. Here are some pitfalls you can fall into. I think honestly the thing that's could probably use the most work about this is we haven't spent a whole lot of time tuning compile time, right? So it takes to compile our runtime system, which is only 15 or 20,000 lines of code, takes a good 20 or 30 seconds, and that's a long time for that amount of code, right? And so building the entire X10 system from scratch on my laptop takes me 5 minutes, right? Which is a while. Okay. Anything? Yeah.
So what's from the language designer perspective, what do you think about the relationship between the use? I mean, what do you think about the language designer is driven by the designer itself or driven by the application program?
I mean, I think initially the language design was driven a lot by conceptually this is what we think we need, and a lot of the design that's happened over the last few years has been driven by we're actually using the language, and we find places where our ideas didn't work so well. We find other places where they did, and in particular we've gone through, I think we're on our third different distributed object model, and that was completely based on trying things and discovering why they didn't work and then changing it again. And I think now we actually have a language model, a distributed object model that actually works very well, but it took several rounds to get there, and it was important to be using the system to get there. Yep, Dennis?
So in the same more or less style question, I noticed that in your little example, you had not so many imperative updatable variables and many valves.
Yes.
Has the programming style gotten more functional over the years?
I think I mean, local variables, I do this in Java too, I guess. Some of it's just style. Yeah, I mean, things are, especially when on local variables, things tend to be functional because it's convenient. I mean, we still do, a lot of our computations are based on heap data structures that we mutate in place because they're arrays, they're octrees, they're sparse graphs, they're things that need to be updated. So at that level it's not, but sort of at the local computation level it's very common to have a bunch of local variables mutate and to the default. Alright, so I think what I'm going to do, so we don't get too late for the break, is I'm going to spend about 5 or 10 minutes just telling you about some of this stuff, and then we'll get to the break a little bit late, and I apologize for that.
No, I'll apologize because I started too late.
Okay. All right. So anyways, so what's happened since X10 2011? And so we have had 2 major releases, and at the workshop last year, and we did the 2.20 release. We promised we wouldn't change the language in a backwards compatible way, and we've actually managed to keep that promise, and we're going to continue to keep it. So you can sort of build things in X10 without worrying that we're going to yank the rug out from underneath you yet again. A huge piece of work that's been going on by Kawachi-san and his colleagues in Tokyo is working on Java interoperability. So in a current SVN head, there's actually tech preview. There's a tech preview in the last release, and the main thing that's missing actually now is documentation and examples. The functionalities there. I'm going to tell you a little bit about that on the next slide. There's been a lot of work in Managed X10 in terms of performance improvement. We did a complete rework of the serialization protocol, which got us a huge gain in efficiency for multiplex computation. And then Kawachi-san is going to be telling you about these 2 pieces of activity in papers today. And then I'm just going to tell a little bit about some of the application work we've been doing at X10 at IBM to give you a sense of the things we're doing. All right, so this X10 Java interoperability, we've been using it a fair amount over the last year to build our main memory MapReduce engine, which David Cunningham will be talking about this afternoon. All right, so obviously, maybe not obviously, we haven't solved the compiling Java to run well with native code problem. So Java interoperability is with the managed backend only. It's not with the native backend. But the basic idea here is for X10 to call Java, you just use an import statement in your X10 source file to import a Java type, and then you just use it. Right? So our compiler can parse Java class files and build up a representation of that type. It knows what the methods are, how to construct it. X10 classes can implement Java interfaces, and that's a way you can sort of interact with Java libraries that expect implementations of interfaces to be passed into them as callbacks or other kinds of things. So basically this pretty much works. There's some places that are a little bit ugly, so we've taken, so to actually create a Java array as opposed to an X10 array, you have to call a helper method on an X10 class, which sort of encapsulates the little piece of Java code that does a new array. So there are a few cases like that where there's some indirection. But to the first approximation, if you have a Java library you want to use, you just import it, and start using it, put the jar files in your class path, and it's fine. In terms of Java calling X10, so now you've written some code in X10 and you want to call it from Java, that also to a large extent just works, but we're still doing some design work with our generics, so we're not entirely sure that the code generation strategy we have for generics now is the one we want to live with forever. So what we're going to promise for the next release is that the calling non-generic static X10 methods from Java is stable, and you can keep doing that, and that won't change out from underneath you. And you can call this, and it'll work, and it's a little bit ugly because there's a fair amount of name mangling and extra parameter passing that's going on if you're calling a generic method, but we're not going to promise that that's going to be stable. But you can do it if you need to. And the other big restriction is when you call from Java to X10, the X10 code internally can create asyncs, do all sorts of things, but it can't create any free-floating asyncs. So if you have to have a finish before you say async, because we're not really prepared to let async sort of float out into the Java runtime, because we don't have the structures up there that actually let us keep track of them.
But couldn't you just sort of say that implicitly main has a finish?
We do, but so part of what we want to do here is we don't want to insist that the X10 main is on top.
Oh.
So part of what we're doing here is you're going to have a Java program that you've written, and it's doing all kinds of stuff, and it wants to call an X10 library, and we're not going to insist that X10 is on top.
Good point.
So that's why this restriction is here. There's probably some way to finesse that somehow. You can imagine a free-floating async that may or may not terminate before the program terminates. And that's something to sort of think about as people have more experience with this. Okay. So, sorry, any more questions about the Java interoperability? All right. I'll just tell you a little bit about this global matrix library. So this is something a library we built in X10. We released open source at Uppsala last year. And it's about 30,000 lines of X10 code. So it's an example. So it does a bunch of things. So one thing that it does, it provides to the X10 programmer a library of dense and sparse matrix representations with a variety of ways of distributing them. So it's distributed sparse and dense matrices. There's a bunch of layers to this global matrix library. And it works on both back ends. We've wrapped the BLAS library, so some of these core matrix operations go down to BLAS or LAPACK if you have it on your platform. If not, we have a simulation of those. And so you can do a whole bunch of stuff here. And the key ideas for this is just one slide, an example. So here's this algorithm you might like to do, Gaussian non-negative matrix multiplication. It's at the core of some machine learning algorithms. Mathematically, it's this, right? And what you're doing here, you're dealing with some sparse matrices where D is about 100 million entries in sparse, or D is about 100 million entries, W is about 100,000, but very sparse, and you want to do this iterative computation on it. So here's the mathematics, and here's the X10 code you would write to implement that loop using the global matrix library. So what we're trying to give to the programmer is the programmer sort of has to do some work to set up the matrices, which I didn't show you there, and decide how they want to distribute the data. But then once they've done that, you can operate on them as if they were sequential, and then each of those calls internally deals with spawning activities across all the nodes, doing the computation, doing the collective operations, and all that kind of stuff. So we're trying to build a library that will let people do high-level matrix operations. And so this is potentially interesting either if A, you want to do high-level matrix operations, or B, you sort of want to look at what it would take to build, and what we've done to build a library in X10 that's fairly big, gets some good performance, and is providing this kind of abstraction to people. This is allowed on the SourceForge site.
Again, a very functional style in the red box.
Yes, yeah. Yeah, it's a functional style, although it's not obvious from this, but some of these operations are doing in-place update of the, I mean, you can't afford to do copies of used matrices, so depending on these operations, some of them are actually updating in place one of the arguments. And that's a decision that was made in this library. You don't have to make that if you wanted to deal with copying everything.
But it's beginning to look a lot like MATLAB.
Yeah, and that's one of the things I think would be very interesting. We've been talking to Lori Hendren about it a little bit. Actually, she's doing some work with MATLAB. This could potentially be a compilation target for MATLAB, right? Or at least some piece of MATLAB to compile to get a distributed MATLAB implementation or MATLAB-like language. You know, here's some distributed matrices you compile into. So, and then Lori has a student working on that, so you might want to, if you're interested, you could talk to her, maybe you could push it along. Okay, so the other thing we've been doing that I think is kind of cool is we've been doing some work on parallel stat solving with some people in Watson who care about stat solving. And the key thing is, so one way of doing a parallel stat solver is this thing called portfolio stat solver. So you take a whole bunch of sequential stat solvers with different algorithms, feed them different parameters, and throw them at the same problem, and let them talk back and forth to each other about what they've learned. And so what we've actually done is we've got this framework called SAT X10. There's a tools demonstration paper at the SAT conference, I think next week or the week after, and the code will be released open source. And basically it's just a very small X10 program, a few hundred lines of X10 that basically start up a whole bunch of parallel stat solvers across a distributed system and then deal with the communication in X10. And we compile that with a native backend, and we link in all the CSAT solvers more or less unchanged. And so you get a portfolio stat solver without very much work. So this is an architecture slide. Just to give you some results. So this is showing running 8 stat solvers on a single node, sharing clauses of length 1 and length 8. And what this is showing is the number of problems solved along the y-axis and time on the x-axis. And so as time, as you sort of go along, you're solving more problems. And if you actually share bigger clauses, you learn faster, which is something they weren't sure of. Most parallel stat solvers these days only share clauses of length 1. So this is something the SAT guys wanted to explore with. And this is showing now we're running across 8 places on 8 hosts, or 64 places on 16 hosts. It basically says you add more machines, it gets faster. I don't have slides for them now. We've actually been running this up to 1,000 cores on some problems, and still getting some speed ups on some of the very hard problems. So, I think we're kind of excited about this just as a way of using X10 as a little glue language to let people write some parallel code without having to use MPI, and it's been very effective. And the other thing that was sort of nice is we spent probably 2 or 3 days hand-holding the SAT guys, teaching them X10, getting it to work, and now they're actually changing the communication things themselves. They've done a hub and spoke kind of communication instead of a broadcast, and they did that themselves. So it's been fairly successful. And then, welcome.
Thank you. Final questions.
Final questions for now. I'm here all day.
Yeah,
go ahead.
For future addiction, does the X10 target environment include accelerator environments such as maybe a CUDA or Intel Mac?
And so we have a CUDA backend now, and what it mostly does is loop kernels and some things about that. There's a paper about that, I think at X10 last year, is that right?
Yes.
Yeah, there's a paper about it at X10 last year, at the X10 workshop last year, that's available online. And that's still supported, but we haven't pushed it much further than that, so we haven't looked at Intel Mike yet. But I think the basic programming model concepts are pretty decent, where you model the places as GPUs, and you do add statements to transfer control from one to the other, to go from the CPU code to the GPU kernel, and then the compiler basically does the DMAs for you to move the data back and forth, and there's a few primitives to allocate memory on the GPU. And also, you basically reinterpret Rails and X10 as Rails and floats as if they were arrays in the GPU.
Other questions?
Jennifer?
Which version of that, and I know, which version of X10 do you use?
Do I use?
What version or which is?
Right, so we use both, and so it depends what we're doing. So we're doing a lot of work with MapReduce and with 1 or 2 other internal workloads where what we're really trying to do is take existing Java code and scale it across the cluster. And so then we use the managed backend. For the HPC stuff, we use the C++ backend. And some of that's because those codes are simpler, they're not as object-oriented, and some of it is that we actually need them to work on, we run in the Blue Gene, there's no Java on the Blue Gene, and even on the Power 7-based systems where you can run Java on the nodes, in principle, it tends not to be there. And also, I'm a little bit leery, honestly, of the jitter invoked by the JIT and the garbage collector across. You're running 10,000 JVMs that are coordinating with each other. I think it would get a little dicey.
So for large-scale stuff, C++.
Yeah, for large. Yeah, for like up to 100 nodes, the Java stuff is managed backend is fine.
Okay.
All right.
Thank you.
All right. Thanks.
Coffee is outside.
Excellent.